Thank you. Thank you, everyone. Good morning. Welcome to everyone online, and thank you. It's a wonderful opportunity to be here in person today. I'm delighted to make the trip across from Western Australia for this important meeting. So I also need to acknowledge the Whadjuk people of the Noongar Nation as the traditional custodians of the country and waters on which Murdoch University stands, and we pay our respects to the Noongar elders past and present. So, as Professor Rainey Smith eloquently stated, as we're starting out, it's starting to understand the importance of sleep for dementia risk. And we can divide risk factors for dementia into non-modifiable and modifiable. And the non-modifiable, of course, is female sex, increasing age, and genes such as the apolipoprotein E4 allele. Whereas a recent Lancet Commission, which was published in 2020, identified 12 modifiable risk factors for dementia, which account for around 40% of worldwide cases. And when we consider these factors across life stages, in early life, less education is associated with increased dementia risk. In midlife, it's hearing loss, traumatic brain injury, obesity, hypertension, and high alcohol intake, which increase the likelihood of developing dementia in later life. And in later life, the list includes smoking, depression, social isolation, diabetes, physical inactivity, and air pollution. But what's striking about that figure, of course, is yes, 12 modifiable risk factors accounting for 40% of dementia cases around the world. But what about sleep? That percentage is likely to increase as more evidence becomes available, and certainly our focus here is considering the role of sleep in dementia. So my work is predominantly focused on Alzheimer's disease, the most common cause of dementia, accounting for around 70% of cases. And as Professor Rainey Smith mentioned earlier, it's been recognized for a very long time that disturbed sleep is a symptom of Alzheimer's disease. And it's not surprising when we consider how degenerated the brain is when someone is diagnosed with Alzheimer's disease, and all the complex systems, neurotransmitters, and regions of the brain that are associated with sleep. However, a large and increasingly large body of evidence is starting to suggest that sleep is certainly a risk factor for Alzheimer's disease and dementia due to Alzheimer's disease. And that's because the neuropathology that accumulates in the brain when someone is on the pathway to getting Alzheimer's disease is at increased risk of developing when someone has disturbed sleep. And this bidirectional relationship has been turned. And this is where my program of research is particularly focused. So understanding how suboptimal sleep contributes to cognitive decline and the accumulation of neuropathology in the brain, which increases risk of Alzheimer's disease. So my research program can be divided into two parts, essentially. So the first of which utilizes observational data from a number of well-characterized aging cohorts. And I'm using that data to investigate the association of sleep parameters, so quantity and quality, and how that relates to trajectories of change in terms of cognitive function and biomarkers of brain health, such as amyloid accumulation, tau accumulation, and also glucose metabolism. And using that data, I'm trying to understand which sleep parameters are particularly important for changes to cognition and markers of brain health. Are mean estimates of sleep as important as night-to-night variability? What's most useful in terms of screening for future dementia risk? Is it self-report measures? Is it objective measures? Or is it the difference between the two, which we're referring to as sleep discrepancy? As well as understanding factors that influence these trajectories, such as the ApoE4 allele, which I mentioned before, the most common genetic risk factor for Alzheimer's disease, as well as other comorbidities, cognitive reserve, age and gender. And we've started to undertake some work looking at the role of sleep disorders. At the moment, we're focusing on obstructive sleep apnea as well, and how that can influence those trajectories of change in terms of cognitive outcomes and biomarkers of brain health. So I've been showing this picture a little bit recently, but I think it's quite poignant. So we've got a long journey ahead of us. It's akin to climbing Mount Everest, but I've got a great team. We're well equipped. We're certainly enthusiastic, and we're taking those first steps towards understanding the importance of sleep as a risk factor for Alzheimer's disease. So I'll start just by showing some of the data that we've been accumulating within the ABLE study. So ABLE is the Australian Imaging, Biomarkers and Lifestyle Study of Aging. It's a study that is now in its 15th year. We assess individuals every 18 months. We assess their cognition. They undergo amyloid and tau scans, more recently SMBT1 scans for looking at monoamine oxidase B in the brain. We also collect blood samples from these individuals, and we have a wealth of lifestyle data. In recent years, I introduced some sleep measures to this cohort. So we've got the Pittsburgh Sleep Quality Index, the Epworth Sleepiness Scale. Also, we have the Stop-Bang questionnaire, and we're now starting to collect objective data using wrist-ox and gene actives. Previously, we've had hip-mounted actigraphs as well to collect data, but it's been challenging trying to transform that into meaningful measures of sleep. So this work here, which is focusing on amyloid accumulation in the brain, as I mentioned, that's one of the hallmarks of Alzheimer's disease. And we know that it starts to accumulate in the brain some 20 years before individuals are diagnosed as having Alzheimer's disease. And my PhD student, Louise Pivac, who's here in the audience and will be presenting in the next session, so I won't go into too much detail, but safe to say that she's been doing some tremendous work understanding the relationship between self-report measures of sleep and rates of amyloid accumulation in the ABLE study. And she has shown, as I said, I won't go into too much detail, but she's shown that sleep efficiency is particularly important for predicting the rates of amyloid accumulation, with poorer sleep efficiency being related to much faster rates of amyloid accumulation. And she's extended this work to look at cognitive performance in this cohort. And she's seen some very interesting genotype-dependent relationships between sleep and rates of cognitive decline in these community-dwelling older adults. And these graphs here, they just show the relationship of cognitive performance to some sleep parameters in cognitively unimpaired individuals. So there are 526 individuals who are all cognitively unimpaired at baseline. They're 60 years of age or older. And looking at the relationship between sleep efficiency on the left-hand side and attention, we can see that poorer self-reported sleep efficiency, which was assessed using the PSQI, was associated with a much faster decline in attention, regardless of whether someone carried that E4 risk allele for Alzheimer's disease or not. So it really was playing a very important role in terms of predicting the rate at which someone's attention would decline over some 8 years of follow-up. And then on the right-hand side here, we can see the relationship between sleep quality and episodic memory. And what we were seeing is that poor sleep quality was associated with a faster decline in episodic memory, particularly in E4 carriers, and poorer performance in non-carriers compared with good sleepers. But that fast rate of decline that we can see on the very right-hand side graph is quite striking, I think. And as I mentioned before, it's not just mean sleep that we think is important. We think that night-to-night variability in sleep it has an important role to play in someone's likelihood of developing Alzheimer's disease down the track. And certainly we're revisiting some of our cohorts to try and understand this relationship in greater detail. And I have a PhD student, Alex Miladinovic, I'm sorry, Alex, for butchering your surname, who I co-supervise with Professor Romola Bucks and Associate Professor Mike Weinborn at the University of Western Australia. And he has been looking at the role of night-to-night variability in sleep and how that relates to Alzheimer's phenotypes. And he has seen that individuals who have a higher night-to-night variability in their sleep have a much higher level of amyloid in their brain at baseline, and this level stays high over time, much higher than individuals who have low night-to-night variability in sleep. And you can see the dotted line there, which is the what we refer to as the threshold for amyloid positivity. And actually that number has revised down since these results were generated, down to 20 centiloids. But regardless, you can see that the individuals who have high night-to-night variability in sleep start off at baseline with a centiloid of some 75, which is approaching what we might expect to see in Alzheimer's patients, which is striking when we consider the fact that these individuals are all cognitively unimpaired. So they are likely on the pathway to Alzheimer's disease. And extending that work to cognition, Alex showed that individuals with that high and night-to-night variability in sleep also have much poorer performance and measures of recall and recognition. And when you look at the mean difference between those groups, you can see that there's some 1.5 or 1.25 standard deviation units and a difference in performance between the two groups for recall, and around 0.64 standard deviation units in difference between their recognition scores. So that really is a very significant difference. And again, it leads us to think that we really should be considering night-to-night variability in sleep in terms of predicting an individual's likelihood of being on the pathway to developing Alzheimer's disease in the future. So this work, which has been undertaken in collaboration with Professor Ralph Martins, his postdoc, Dr. Remy Chatterjee, and Steve Pedrini at Macquarie University and Edith Cowan University, has been looking at blood-based biomarkers of Alzheimer's disease and dementia in ABLE and relating it to some of our sleep data. And what we have seen using the stop bang as a screening tool for obstructive sleep apnea risk is that individuals who are in the high OSA risk category, as assessed using stop bang, seem to start at baseline with higher levels of GFAP, or glial fibrillary acidic protein, which is a filament protein expressed in astrocytes. And we know that when the levels of this protein increase, it's usually an index of gliosis or reactive or activated astrocytes, and it's also a marker of slow developing neural damage. So what we see at baseline is what we would necessarily expect to see. So we might expect that individuals in the high OSA risk have higher levels of reactive astrocytes compared to individuals in the low or intermediate risk groups for OSA. But what is striking is that over time, the low and intermediate groups for OSA risk continue to show an increase in the levels of GFAP, so an increase in the levels of reactive astrocytes. Whereas those individuals in the high risk for OSA show this striking reduction in the levels of GFAP over time. So we're trying to understand what's going on here. We don't know the answers yet, but we think that it might be related to where someone is on that continuum of disease and on the pathway to developing Alzheimer's disease. And I noticed that at AAIC, so the Alzheimer's Association International Conference, which occurred last month, there was a nice graph from a group in the UK, which showed that the changes in GFAP levels at each stage of the Alzheimer's continuum, so from moving from preclinical to prodromal to actual full-blown Alzheimer's disease, the change in GFAP levels was certainly not linear. It started off with a very rapid increase in the preclinical stage, reaching a peak, and then it started to drop off rather rapidly. So perhaps these results that I'm showing here are suggestive that these individuals with high OSA risk are further along the pathway to developing Alzheimer's disease than their counterparts in the low and intermediate risk groups. But we've certainly got more work to do there to understand that. And this work was possible through a CRE collaboration and utilizing the leading technology that Professor Martins has in his lab over at Edith Cowan University, the Simoa machine, which is an ultra-sensitive tool for assessing levels of these biomarkers in blood samples. So we also have some data that was collected using SMBT1 in ABLE. So we're still trying to crank through the analysis at this stage, and we're awaiting the next tranche of imaging results. We've got some exciting preliminary findings so far, but I think with a larger sample size, we're being more confident in the findings. So what we're looking at is the highly selective monoamine oxidase B tracer SMBT1, and that tracer binds to reactive astrocytes. And that's because the monoamine oxidase B is present in the outer mitochondrial membrane of reactive astrocytes. They overexpress it. So again, we're taking advantage of the wealth of data that's present in the ABLE cohort, and excited to see what those preliminary findings tell us in the future. So the Lancet Commission, which I mentioned before, has these 12 risk factors which are proposed to account for around 40% of dementia cases. But we certainly think that sleep should be added to that list. I'm sure that all of us in this room agree about that. But we need to collect more data. We need more evidence to be able to have sleep added to the next iteration of that Lancet Commission. And we need data from intervention studies as well to help guide that evidence and to broaden that evidence. And that's where the second half of my research program comes in. So conducting some intervention studies to determine to what extent improvement in suboptimal sleep following an intervention improves cognitive function and also impacts the trajectories of biomarkers of brain health, which I've mentioned before. So amyloid, we've also got glucose metabolism and MRI. And we're investigating candidate mechanisms that underlie the causal relationships between sleep improvement, post-intervention, and improvements in cognition. We're going to be looking at sleep architecture, also looking at between subject response in intervention. So again, looking at ApoE genotype, comorbidities, and differences between gender and age groups in response to the intervention. So one of the intervention studies that I am leading, which is aimed at understanding the effect of improved sleep on memory and thinking and markers of brain health, is called the SIS study, so Sleep Improvement Study. And we have participants who have poor sleep come in, and we undertake sleep assessment on them using polysomnography. We also collect actigraphy data and some self-report questionnaires. We have them undertake an extensive neuropsychological test battery where we collect data about their memory and thinking. We also have them undergo 3 types of neuroimaging, so MRI, glucose metabolism PET, and amyloid beta PET. And we collect blood from them so that we can undertake ApoE genotyping, and also so that we can look at the blood biomarkers, some of which I've mentioned previously. We then have these individuals go into an intervention, and we are utilizing cognitive behavioral therapy for insomnia, as Sharon mentioned earlier, the gold standard for insomnia worldwide. And this component of the study is led by Dr. Melissa Ree, who is a worldwide authority on CBTI, and she'll be presenting later today, I believe. And we have these individuals undertake the CBTI course, and we assess them again at 9 months, and once again at 18 months we have them come back in. We reassess their sleep, their neuropsychological functioning, their brain imaging, and we collect another blood sample. And this work is undertaken in collaboration with Professor Romola Bucks and A. Prof. Mike Weinborn at the University of Western Australia, and also with Professor Ralph Martins for the blood-based biomarker work. And we've just started a 36-month assessment now. So we've had, I think we've got 2 groups left to run this year before the baseline assessments are complete. So hallelujah, I'm very happy for the fact that the baseline will be over. We're also concurrently undertaking the 18-month assessments, and we've also got some people coming in now for the 36-month assessment. So we are well on the way, and we're anticipating our first baseline paper to be published early next year. The other intervention study that we're looking at is part of the AU-ARROW study. So the AU-ARROW study is led by Professor Ralph Martins, and it's a worldwide initiative referred to as the FINGERS initiative, which looks at the effects of a multimodal lifestyle intervention on Alzheimer's and dementia risk. So the multimodal lifestyle intervention includes dietary guidance, physical activity, as well as reducing cardiovascular risk factors. And this work has been led in Finland by Mia Kivipelto. And there are also now groups in the US and throughout the world, and as I mentioned here in Australia, led by Professor Martins, which are looking at how this multimodal lifestyle intervention can lessen the risk of developing dementia in the future. And in conjunction with Professor Sharon Naismith, she and I have been very fortunate to be able to add a sleep arm to the ARROW study. And we are testing whether this 12-month, well, actually will be 24 months in total, but we've said that we'll assess sleep after 12 months, whether this 12-month intensive lifestyle intervention improves measures of hypoxemia and sleep fragmentation, and to assess the degree to which this longitudinal intervention effects on sleep predict changes in cognitive trajectories, which are assessed as part of this study test battery, and also to assess the degree to which the intervention effects on sleep predict dementia biomarkers, and once again looking at the individualized response to the intervention and whether it's someone's greater improvement in sleep which is predictive of their greater benefit in terms of the intervention. So we're using watch packs to assess the oxygen desaturation overnight, and we're supplementing that. Well, these watch pack devices are very nice, and they give us a lot of data. And here are some of the reports that they generate, including our AHI and central AHI, as well as time spent in sleep stages, body position graphics, and help us to understand someone's oxygen desaturation overnight and other data. And we're supplementing this with Fitbits, which give us a continuous measure of sleep in the home environment over 7 days and nights, and also will help us assess the night-to-night variability in sleep, which, as I mentioned before, we think is very important for understanding the relationship between sleep and brain health. Another study that we will be getting underway in the very near future is a collaboration with the RAIN study, and that involves Professor Romola Bucks, the director of the RAIN study at UWA, Professor Rainey Smith, and Professor Ralph Martin, who are all here in the room. We are trying to understand when in the life course it's most important to intervene for the greatest cognitive benefit. So we are getting some money together to assess sleep using polysomnography in the fourth decade of life, and also in their parents. So the benefit of the RAIN study is that it's followed individuals from in utero up until the 30 years of, well, in their 30s now, so about 33 years of age. And also it's been collecting data on their parents. So we have this wealth of data from into their 4 decades worth of data, where we can start to model this data and understand how sleep is related to cognitive trajectories over the life course. And also we'll be investigating the candidate mechanisms underlying these causal relationships. So we'll be looking at the blood-based biomarkers using the Samoa technology under Professor Martin's leadership, and also we'll be looking at some metabolomics profiling and utilising the resource of the Australian National Phenome Centre at Murdoch University. And we're hoping that this work will provide insight around when to intervene, and as well as guiding potential future therapeutic targets. And I'd just like to finish by thanking all the individuals on this slide here. I'm very fortunate to be able to work with some great people, very talented people, including 2 of my students who are listed on the slide there, Louise and Alex, and all the individuals here contribute to the wealth of data that I'm able to utilise to address these very important research questions. And with that, I'll finish. Thank you.